In Module 3, we explored use cases for backup and archiving and disaster recovery. Now in Module 4, we'll take a look at use cases for web, mobile, and social applications and big data. Also in Module 4, we will take a look at pricing tools that help you estimate AWS costs and make the most efficient and cost-effective choices for your AWS services. As we explore web and big data solutions, we will examine AWS cloud architectures, comparing them to traditional infrastructures and associating the specific AWS services used to build each solution. Inherent to each solution are potential migration strategies and technical implications. Web, mobile, and social applications. Whether you're running your company's website, hosting a content management system, developing social media apps, or just creating an internal SharePoint site, hosting your website in the AWS cloud is fast, easy, and low cost. You can easily deploy and maintain websites and apps that always run fast using the AWS comprehensive set of on-demand compute, storage, database, and application services. AWS provides developers with a platform for delivering their applications that is flexible, highly scalable, rapidly deployable, and low cost. One of the great advantages of cloud computing is how easy it is to scale up or down. AWS provides you with the tools and the ability to respond to spikes in demand in an automated fashion. That way, when your app goes viral, you can meet the demands of millions of new users. You can also expand your global reach through the AWS Management Console. AWS is compatible with all devices and the most popular mobile platforms, including SDKs for iOS and Android. AWS is platform agnostic, so that you can use your preferred programming language. AWS provides SDKs for many popular back-end platforms, including Java, Ruby, PHP, Node.js, .NET, and more. No matter which system you choose, it can run on AWS. You can manage your site or application using the many tools provided. For instance, you can easily manage content with the AWS built-in content management system. Businesses around the world are running their social media networks and applications in the cloud to lower costs, improve time to market, and enable rapid scalability. AWS powers some of the world's most popular Facebook apps, including 70% of the top 50 Facebook applications. Because new instances are easy and cost-effective to spin up, you can provision testing fleets just when you need them. You can use the testing fleets to simulate user traffic during load testing in a beta environment. And you can also use these parallel fleets as a staging environment for a new production release. Then quickly switch over from current production to a new application version with little to no service outages. Traditional web architecture presents a variety of infrastructure and architectural issues. For example, all of the components are tightly coupled to one another, which means that you can't easily insert new servers to handle unexpected traffic, and the entire system has a limit to how much it can handle. In this diagram, you can see the web load balancer that is distributing traffic to the web servers. There is a web tier fleet of machines handling HTTP requests. Then there is a backend firewall that is limiting access to the application tier from the web tier. Behind the backend firewall is the application load balancer that is spreading traffic over the application server tier, a fleet of machines handling application-specific workloads. Caching server machines can be implemented at this layer. Next, the data tier comprises database servers, with the master and slave running separately and providing network storage for static objects. Outside of the larger firewall, periodic backups are stored on tapes, typically managed by a third party. Let's see how this differs from architecting a web application on AWS. In this example, the application and web servers run on EC2 instances belonging to an EC2 security group. The security group acts as an exterior firewall for the EC2 instances. An auto-scaling group is used to maintain Amazon EC2 instances and spans over multiple availability zones, or AZs. This protects against potential failures if an AZ becomes unavailable. The ELB load balancer is associated with the auto-scaling group to ensure that traffic is distributed evenly among the Amazon EC2 instances. The database tier consists of Amazon RDS database instances located in multiple AZs for failover protection. Amazon RDS provides automated backups to Amazon S3, which stores backups and static content. Because users may be globally distributed, or because a lot of users may visit the site at one time, high-volume static content is edge cached for better performance by using Cloudfront. Additionally, Route 53 can be used to provide secure and reliable routing. Unlike a traditional web hosting model, inbound network traffic filtering should not be confined to the edge. It should also be applied at the host level. Security groups provide this kind of filtering, act as an inbound network firewall, and are provided as a feature of your EC2 instances. In the AWS Management Console, you can specify the protocols, ports, and source IP ranges that are allowed to reach your EC2 instances. In this example, the security group for the web server cluster might allow access for any host only over TCP on ports 80 and 443 for HTTP and HTTPS, and from instances in the application server security group on port 22 for SSH for direct host management. The security group of the application server cluster, however, might allow access from the web server security group for handling web requests and from your organization's subnet over TCP on port 22 for direct host management. Moving a web application to the AWS cloud requires some DNS changes to take advantage of the multiple availability zones that AWS provides. To help you manage DNS routing, AWS provides Amazon Route 53 as a DNS web service. Queries for your domain are automatically routed to the nearest DNS server, providing the best possible performance. Route 53 resolves requests for your domain name, shown here as www.mywebsite.com, to your load balancer and your zone apex record, which is mywebsite.com in this case. Hardware load balancers are a common network appliance used in traditional web application architectures. AWS provides this capability through the Elastic Load Balancing Service, a configurable load balancing solution that supports health checks on hosts, distribution of traffic to EC2 instances across multiple availability zones, and dynamic addition and removal of Amazon EC2 hosts from the load balancing rotation. Elastic load balancing can also dynamically grow and shrink the load balancing capacity to adjust to traffic demands while providing a predictable entry point by using a persistent CNAME. Elastic load balancing also supports sticky sessions to address more advanced routing needs. If your application requires more advanced load balancing capabilities, you could run a software load balancing package on your EC2 instances. You could then assign elastic IP addresses to those load balancing EC2 instances in order to minimize DNS changes. Amazon Cloudfront can be used to deliver your website, including dynamic, static, and streaming content using a global network of edge locations. Requests for your content are automatically routed to the nearest edge location. so content is delivered with the best possible performance. It is optimized to work with other AWS services, such as S3 and EC2. Cloudfront also works seamlessly with any non-AWS origin server that stores the original, definitive versions of your files. Many web applications contain some form of persistence, usually in the form of a relational or NoSQL database. AWS offers both relational and NoSQL database infrastructure. Alternatively, you can deploy your own database software on an Amazon EC2 instance. You can install your choice of relational database management systems on an EC2 instance and manage it yourself. In this scenario, you manage everything, just as you would on a traditional on-premises system. An additional consideration when managing your own database software directly on Amazon EC2 is the availability of fault-tolerant and persistent storage. For this purpose, we recommend that databases running on Amazon EC2 utilize Amazon Elastic Block Storage volumes included with your EC2 instance. These are similar to network-attached storage, which will remain available even if the database host fails. Numerous storage systems are available with AWS, and the one you will use depends on the type of data you're going to be storing. This table summarizes the types of data that are commonly found in web applications and the appropriate storage solution for each. As shown in the AWS Web Hosting Architecture model, multiple auto-scaling groups can be created for different layers of the architecture, so that each layer can scale independently. For example, the application server auto-scaling group might scale out and in according to CPU utilization, whereas the web server auto-scaling group might trigger scaling out and in response to changes in network I/O. Auto-scaling also works directly with Amazon CloudWatch for metrics data, and with the Elastic Load Balancing service to add and remove hosts for load distribution. For example, if the web servers are reporting greater than 80% CPU utilization over a period of time, an additional web server could be quickly deployed and then automatically added to the Elastic Load Balancer for immediate inclusion in the load balancing rotation. Auto-scaling triggers can be set both to grow and to shrink the total fleet at a given layer, to match resource utilization to actual demand. In addition to the auto-scaling service, Amazon EC2 fleets can be scaled directly through the Amazon EC2 API, which allows for launching, terminating, and inspecting instances. Deploying instances in multiple availability zones helps you achieve redundancy. Availability zones are physically distinct locations that are engineered to be insulated from failures in other AZs. They provide inexpensive, low-latency network connectivity to other AZs in the same region. Lastly, it is important to ensure that there are provisions for migrating single points of access across availability zones in the case of failure. For example, a database slave should be set up in a second availability zone so that the persistence of data remains. In this video demonstration, you will see a website created and deployed in just 10 minutes. Click to play the video.
Let's explore the process for deploying a simple web application, but doing so in a highly available way by leveraging multiple availability zones, multiple EC2 instances to host the web application, and deploying an elastic load balance in front of all of that to act as our endpoint for users to connect to. To launch new EC2 instances, we have navigated to the EC2 dashboard in the AWS Web Management Console. The first step is to click the Launch Instances button on the main dashboard. This will bring you into the EC2 Launch Wizard, which will take you through each step required to configure and launch your EC2 instances. The first step is to select the AMI that we like to use as the base for your EC2 instance. In this example, we're going to simply use the Amazon Linux 64-bit AMI. The next step in the wizard asks you what size EC2 instance you would like to use. For this example, a T2 micro will be adequate, and as an additional bonus, it is part of the free tier. The next step asks us to configure our instances. In this step, we need to determine how many instances we would like to run and which VPC we would like to place them in. In addition, what we're going to do today is make sure that we assign each instance to a different availability zone to make sure that we have instances spread across both the availability zones in the region we're in to ensure that we have high availability architectures. The last piece of this part of the wizard asks us for the user data. The user data is a way for a user to pass a script or values into an EC2 instance as it boots up. This can be used to change the way that an EC2 instance behaves. It can be used to inject values into scripts already on the AMI and many other use cases. In today's example, all we're going to do is pass in a simple bash script to install a couple of Linux services, namely HTTP or Apache and PHP. And we're going to download a very simple PHP application from S3 and explode it onto the file system of the web server to be our web application. The next step in the wizard is to configure the storage for the EC2 instance. In this case, we have a single EBS volume of 8 gigabytes provisioned on general purpose SSD storage. We could provision additional EBS volumes, and if this was an EC2 instance type that had ephemeral storage, we could also configure the ephemeral storage here as well to be presented to the running instance. In this case, though, we need to make no changes, so let's move on. The next step in the wizard allows us to add metadata tags to our EC2 instance. These can be used for a variety of purposes. The special tag with the key name will actually show up in the EC2 Web Management Console and make it easy to identify each instance that we have running in a particular region, so it's a good idea to use it. In this case, we're going to tag it as being in availability zone A so we can distinguish it from the other application server that will be running in availability zone B. The next step in the wizard will allow us to configure a security group to be associated with our EC2 instance. A security group is essentially the same as a stateful firewall. We must configure all the rules to allow traffic to be able to access or get to the EC2 instance. So in this case, being that it is a web server, we must open up port 80 to accept HTTP traffic. And we're going to do that by defining a brand new security group. We're going to reuse this security group when we launch our second EC2 instance. We've now reached the final step of the launch wizard. It's a chance for us to review all of the settings we've made so far for our EC2 instance. And when we're happy, we can simply click the launch button. Just before launching the EC2 instance, the wizard asks us one final question as to whether we want to associate an SSH key with the EC2 instance. So this would allow us to SSH into the web server if we needed to troubleshoot the box or make any configuration changes on the instance. So we can go ahead and acknowledge that and associate a key called default. That's the key that's in my region for my account. Keeping in mind, though, that we did not open up port 22 when we created the security group. So if we did want to SSH into this box, we'd have to go back and edit the security group and open up port 22 for SSH traffic. Once we click the Launch Instances button, the launch process begins. We're taken to the launch status screen, which shows us the unique identifier for the instance that is launching. However, the instance is not ready for access, and the launch process will take a couple of minutes. We can click on the View Instances button to return us to the EC2 dashboard. We can see on the instances screen that we now have one EC2 instance in our region. However, it is in the pending state and is not yet ready for us to access. So while that finishes provisioning, we can go ahead and get started getting our second instance in availability zone B up and running. Configuring the second instance is almost identical to the first instance with a couple of minor differences. We use the same AMI and instance size. And when we get to the third screen for configuring our instance details, we need to just make sure that we pick availability zone B this time so that we have one instance in each availability zone. Our user data script for the second instance is 100% identical to the first instance. We're going to configure the instance exactly the same. We're going to install the same packages and we're going to pull down the exact same PHP application from the same location in S3 and deploy it in the same way on the Linux instance. On the storage screen, we leave everything as it is. On the tag screen, we just add a unique value for the name tag so we can distinguish it in the console. This time we use the AZB name so we can distinguish it from the AZA web server we've already provisioned. For the security group screen, we can reuse the security group we just created previously for our PHP web servers. It's going to give us a warning letting us know that we don't have port 22 open, which is okay for this demonstration. We're now at the review screen, and if we're happy with everything, we can click Launch. We see the familiar SSH key question, and we click Launch Instances. If we click the View Instances button, we return to the Instances screen of the EC2 dashboard. We can see that we now have a second EC2 instance running in Availability Zone B. If we copy its public DNS name and switch to a new tab in our browser, we should be able to see our PHP application running. And there it is. Notice that the instance ID starts with 55. If we switch to the tab already open for the Availability Zone A instance, we notice that the instance ID, the public host name, and the public IP address are all different for those two instances. We can now move on to configuring our load balancer to sit in front of our two EC2 instances. Select Load Balancers in the left column, and then click the Create Load Balancer button, which takes us into a familiar wizard type screen. We give our load balancer a unique name. We configure it to allow us to configure VPC options. We can see that the load balancer is configured to accept requests on port 80 and will pass those requests through to instances behind it also on port 80. And then we also tell the load balancer that we want to include instances in both Availability Zone 2A and 2B when we're balancing traffic to different instances. On the security group screen, we can select the pre-configured HTTP-only security group because that is the only traffic we're interested in. This warning tells us that we should probably be using HTTPS, which is probably a good idea, but not really necessary for this demonstration. On the health check screen, we just need to make a slight change to make sure we're hitting the PHP page when we're checking and make sure when the EC2 instances are ready to take traffic. And on this fifth screen, we're able now to actually tell the web server which two instances or which instances we want to have traffic balanced to. So we select the two instances we just finished creating. We can give the load balancer a name, but it's not really necessary in this particular demonstration. And finally, we move on to the review screen. And if we're happy with all of the settings, we can click Create, and the load balancer will begin its creation process. If we click the Close button, it will return us to the Load Balancer console, where we can see we now have one load balancer. If we have a look in the Load Balancer Details section at the bottom of the screen and click on the Instances tab, we will see that we have two instances listed. However, the status of both instances is set to out of service. And that's because right now the load balancer is still starting up, and the two EC2 instances haven't passed their health checks yet, so they're still considered to be out of service, which means the load balancer will not be routing traffic to them just yet. After a short period of time, both instances will be marked as in service, meaning that the load balancer is ready to use them because the instances have passed their health checks. If we go to the description tab of the load balancer console and copy the DNS name of the load balancer and paste it into our browser, we'll be able to see the PHP application being served through the load balancer. We pay particular attention to the instance ID. This time it's the instance starting with EC8 serving the request. But if we hit refresh on the browser several times, we'll see that the instance ID actually changes. That's because the load balancer is actually routing traffic to the different instances behind it, and so we're getting different responses coming back from each instance. At this point, we've finished configuring our application. We've provisioned two EC2 instances running Amazon Linux. We've configured security groups for them that will allow HTTP traffic. We configured the user data for those instances to download a PHP application from S3 when they start up. We have placed them in different availability zones for our HA type configuration. We then provisioned an elastic load balancer in front of those two instances, configured those instances to sit behind the load balancer and configured the health check appropriately. We then waited for the load balancer to acknowledge that the instances were there and were both healthy. And then we saw the effect of using a load balancer in front of those instances where traffic was being routed somewhat equally to both instances just by simply hitting refresh in our browser.
Shazam is the creator of a popular mobile application that helps people identify and connect with media content around them. When a user hears a song or sees a TV program or an ad, they simply use the app to tag it, and the app identifies the media providing information such as song and album title or the name of the TV show or product. Shazam boasts more than 200 million users in more than 200 countries and 33 languages, connecting them to music, TV shows, and merchandising brands. Every week, another 1.5 million people join Shazam. The challenge. Shazam produced a Super Bowl advertising campaign designed to create a massive demand spike while it ran. Anticipating the need to respond with much greater capacity, they looked to the elastic capabilities of cloud technology. Jason Titus, Shazam's CTO, explains, "We considered other cloud providers, benchmarked them, and evaluated how they would build out to handle our capacity requirements. In the end, we chose Amazon Web Services because they have the reliability, support infrastructure, and full suite of services that meets our needs." The AWS Solution. After selecting AWS, Shazam implemented its new solution in only 8 weeks, taking advice from its AWS enterprise support team and ensuring maximum platform utilization. The company primarily relied on Amazon EC2 with an instance type specifically designed for high-performance compute applications. Traffic was distributed across these instances with elastic load balancing. They initially used Dynamodb as a secondary data store for user activity and interaction logs. However, when Shazam realized it could support over 500,000 writes per second, they made their Dynamodb NoSQL database service the primary data store. The company is also using Amazon Elastic MapReduce for large-scale data analysis that can require more than 1 million writes per second. The result, implementing resources from AWS, Shazam enabled millions of fans to tag the entire Super Bowl event, from the game to the halftime show to the advertising campaigns featured. Titus says, AWS gave us the flexibility to bring a massive amount of capacity online in a short period of time, and allowed us to do so in an operationally straightforward way. AWS is now Shazam's cloud provider of choice. Big data. Big data helps you understand drivers in your business and gain actionable insights. Leveraged in real time, it informs strategic decisions for small startups to large enterprises, public administrations, and research organizations. Big data is used for large-scale computing scenarios, such as scientific computing, simulation, and research projects. Big data is used to deliver customized web content to millions of users concurrently, analyze billions of financial transactions daily, create personalized medicine based on patient genetic information, and much, much more. Scientists, developers, and many other technologists from many different industries are taking advantage of Amazon Web Services to perform big data analytics and meet the challenges of the increasing volume, variety, and velocity of digital information. Amazon Web Services offers a comprehensive end-to-end portfolio of cloud computing services to help you manage big data by reducing costs, scaling to meet demand, and increasing the speed of innovation. As huge data sets are collected from scientific equipment, measurement devices, or other compute jobs, they need to be analyzed by large-scale compute jobs to generate result data sets. Ideally, we want results to be available as soon as the data is collected. Often these results are then made available to a larger audience. The life cycle of big data passes through stages of collect, store, process, and analyze. To upload large data sets into AWS, it is critical to make the most of the available bandwidth. You can do so by uploading data into Amazon S3. This can be done in parallel for multiple clients, where each client uses multi-threading to enable concurrent uploads or multi-part uploads for further parallelization. TCP settings like window scaling and selective acknowledgement can be adjusted to further enhance throughput. With the proper optimizations, uploads of several terabytes a day are possible. In some cases, when you are initially uploading data to S3, using HTTP may not be the most efficient option. Some AWS partner solutions allow UDP-based uploads to EC2 instances instead, which then push the data across to S3 within the same region. This methodology can be more efficient for very large data sets. For example, it is often used in video production. Another alternative for transferring huge data sets is Amazon Import-Export, which allows you to send your own storage devices to AWS and have the data transferred directly into Amazon S3 or Amazon EBS volume. Multiple EC2 instances can typically run existing parallel applications, making it possible to process in parallel large-scale jobs. Alternatively, an Amazon Elastic MapReduce cluster could be used to process the data set. Amazon Elastic MapReduce utilizes a hosted Hadoop framework, which processes the data in a parallel job flow. A parallel application may sometimes assume large scratch areas that all nodes can efficiently read and write from. S3 can be used as a scratch area for this case. You can read and write either directly using HTTP or using a fuse layer, such as S3FS or Cloudberry. If the application expects a POSIX-style file system, once the job has completed and the result data is stored in S3, the EC2 instances can be shut down, and the result dataset can be downloaded. The output data can be shared with others, either by granting read permissions to select users or to everyone, or by using time-limited URLs. As an alternative to S3, you can use EBS to stage the input set, act as a temporary storage area, and/or capture the output set. During the upload, the concepts of parallel upload streams and TCP tweaking also apply. Additionally, uploads that use UDP may further increase speed. The result dataset can be written into EBS volumes, at which time snapshots of the volumes can be taken for sharing. As an alternative to in this case study, we see how Novartis leverages the massive scalability of the AWS infrastructure to deliver a high-performance computing solution. Novartis is a globally recognized pharmaceutical company based in Switzerland. They conduct research in the development of new drugs for medical advancement. The challenge. On average, it can take 10 years and $1 billion to get a new drug to market. Novartis is meeting this challenge with high-performance computing to accomplish next-generation sequencing, imaging, modeling, and simulation techniques, including virtual screening. In 2013, Novartis chemists wanted to use virtual screening to test 10 million compounds against a common cancer target. They calculated that it would take 50,000 compute cores to process the job. To build a cluster of this size internally would have cost them $40 million, and their existing HPC environment was already utilized at its capacity. They needed to create a new system that was fast, extremely secure, inexpensive, and easy to use. The AWS Solution. Partnering with Cycle Computing and AWS, Novartis built a platform leveraging Amazon Compute, storage, and routing services, including S3, EBS, EC2, and Route 53. They spun up 10,600 EC2 spot instances across 4 availability zones, which equates to about 87,000 compute cores, and they did it in just 2 hours. The results. Leveraging AWS, Novartis was able to dock 10 million compounds. the equivalent of 39 years of computational chemistry, in just under 9 hours, and for a cost just over $4,200. Steve Lister, Novartis Global Head of Scientific Computing, adds, "Most importantly, we actually identified 3 promising compounds out of that simulation. In the coming years, Novartis is anticipating ramping up to petabytes of data per year as they develop life cell imaging computations with the potential of 10 times the amount of data as next-generation sequencing data." AWS is enabling Novartis to innovate as they expand their high-performance data in order of magnitude. Estimating, tracking, and monitoring costs is important to AWS customers. In this last section, we will cover tools to help you do that. The Simple Monthly Calculator, the TCO, or Total Cost of Ownership Calculator, and the Billing and Cost Management Console. Let's first start by looking at how pricing works. Amazon Web Services helps customers save money by using a utility-based model where you pay only for what you use. Each service is priced independently, so you choose only the services you need. You can start or stop any service at any time without complex licensing or termination fees, and with no long-term contracts or commitments. Flexible pricing options also help you optimize your costs. We've described pay-as-you-go, allowing you to pay only for the services you need with no long-term contracts or commitments. You can also pay less per unit as your volume increases and your organization grows. To save you even more, you can invest up front in reserved capacity, saving up to 75% for services like EC2 and RDS. You pay for 3 fundamental components with Amazon Web Services. For compute services and processing power, you pay per hour. For storage, you pay per gigabyte. And for data transfer, you pay per gigabyte for data out. There are no charges for incoming data or data transfer between your AWS services within the same region. Data transfer between AWS services in different regions will be charged as internet data transfer on both sides of the transfer. The outbound data transfer is aggregated across Amazon EC2, Amazon S3, Amazon RDS, Amazon Dynamodb, Amazon SQS, Amazon SNS, and Amazon VPC, and then charged at the outbound data transfer rate. This charge appears on the monthly statement as AWS Data Transfer. Amazon Web Services helps customers save money by using a data transfer between AWS services in different regions. AWS also provides a free usage tier to help new AWS customers get started in the cloud. You can gain hands-on experience with AWS free for 12 months. Just create an AWS account, subscribe to the services you'd like to use, and enter a valid credit card. For more information, go to aws.amazon.com/free. Let's now look at how the Simple Monthly Calculator, TCO Calculator, and Billing and Cost Management Console help you estimate, track, and monitor costs. You can use the AWS Simple Monthly Calculator to estimate your monthly bill. The calculator provides per-service cost breakdown, as well as an aggregate monthly estimate. You can also use the calculator to see an estimate and breakdown of costs for common solutions. Click to play the video giving a demonstration of the Simple Monthly Calculator. To access the calculator, visit awstcocalculator.com.
The AWS AWS Simple Monthly Calculator is a tool that allows you to create estimates of your monthly AWS bill based on your expected usage of various AWS services. Once you have created the online estimate, you can easily share it with your customers or coworkers, and you can also make changes to the estimate to explore the effects on your bill of adopting different possible architectures. The calculator is an online tool and is available at aws.amazon.com/calculator. This is the main calculator screen. On the left-hand side, there's a column representing all of the services that are currently supported by the calculator. In the middle is the breakdown of costs by service and also the billing estimate. And on the right-hand side are some example calculators that you can use as getting started points or learning tools for learning how to use the calculator. In this case, we're going to use the large web application sample as our starting point. The large web application sample is configured using AWS best practices with multiple web servers and multiple application servers configured in an auto-scaling group for high availability. The backend storage tier is made up of Amazon Dynamodb and also Amazon RDS. The application is also leveraging the web serving capabilities of Amazon S3 and also the DNS capabilities of Route 53. You can see that the main part of the calculator has now been populated with the charges associated with provisioning this particular architecture. It includes EC2, S3, Route 53, Cloudfront, RDS, Dynamodb, and it also includes provisioning for AWS support. We can now drill into each of these to explore the exact charges that make up the total bill for each service. For EC2, the charges are made up of the cost of the actual instances running, that's the compute line item, the EBS volumes, that's the provisions block storage attached to those instances. In this particular architecture, they've also provisioned some provision IOPS for those volumes for consistent performance, some EBS snapshots, that's our backups of our stored volumes, some elastic IPs, there's some charges there, and that's only because the IPs were not in use, and the elastic load balances for the provisioning, and then the data crossing over the load balances is also a charge point for EC2. For RDS, the charges are made up of the DB instances themselves, the storage provision for those instances, and some provision IOPS for consistent performance behind those instances. For Dynamodb, there's only the one charge for the provision throughput capacity. For S3, there's a charge for the actual storage of the files in the S3 service, and there's a couple of small charges associated to the actual API calls for interacting with the S3 service. Using the service list on the left-hand side of the screen, we can now drill in and see how each of those line items in the bill were calculated and what resources have been provisioned. For EC2, the bill is made up of several factors. The top section describes the actual EC2 instances that are being provisioned as app servers and web servers, details the type of EC2 instances being used and whether on-demand or reserved instance pricing has been used in the calculation. The second section details the EBS volumes that have been provisioned, the type of volume being magnetic in this case, the size, the amount of IOPS, and how often snapshots are going to be taken, and what the percentage of data is likely to change on a daily basis. In the next section, we have some elastic IPs, the data transfer in and out of EC2, and finally, the provisioning of a load balancer and the charges associated with that. For S3, the charges are broken down into three sections. There's an amount of storage measured in gigabytes per month, a number of requests to the S3 service API, and the total amount of data transferred in, out, and inter-region each month. For RDS, the main charge is the charge for each database instance. In this case, we've got one MySQL instance on a DB and one large instance size. And we've actually turned on the multi-AZ high availability functionality provided out of the box with RDS. For Dynamodb, there are three main charges we're concerned with. We have provisioned 20 gigabytes of storage. We've also provisioned 500 reads and 100 writes of throughput for our table. And we've also provisioned 50 gigabytes of data transfer out for each month. Now that we are happy with our estimate, we can click on the Save and Share button, which will allow us to enter some metadata about our estimate and then provide us with a URL for sharing with people inside of our company or even externally with customers and other partners. Now that we have finished saving our calculator, the tool provides us with a unique URL just for our individual calculator that we can share with people inside of our company or customers and partners outside of our company.
Are you ready to find out how much you could be saving in the AWS cloud? The AWS Total Cost of Ownership, or TCO calculator, will help you to compare the cost of running your applications in an on-premises or a traditional hosting environment to AWS. You describe your on-premises or hosting environment configuration, and the TCO calculator produces a detailed cost comparison. Click to play the video giving a demonstration of the simple monthly calculator. To access the calculator, visit awstcocalculator.com.
The AWS Total Cost of Ownership calculator was launched in 2014. It's available at awstcocalculator.com. The tool allows customers and partners to explore different combinations of workloads that are currently running off cloud and calculate how much it will cost to run them on AWS. Users simply answer a series of questions, including the currency of the dollar value that they want to calculate, whether the current environment is fully on-premise or in a co-location facility, and where their target environment is in AWS based on region. In addition to this, customers can then list out all of the server types they have with basic facts about those servers, including the number of VMs involved, the number of cores per VM, and the amount of RAM available. You can also list out what type of hypervisor and guest operating system are involved. Many rows can be added so that the entire fleet can be calculated in one TCO calculation. The next section on the TCO calculator relates to storage. You can select from different storage types, including NAS and SAN, and specify the raw storage capacity using different units. You can add several rows to capture all of the different types of storage used in the fleet that you're trying to do the TCO calculation for. So far, we've been looking at the TCO calculator in basic mode. Calculator also supports an advanced mode, which allows you to specify even more detail about the fleet that you're attempting to do the calculation for. For the VMs, you can specify characteristics like the total utilization of a VM, how you want to optimize it by, whether it's by RAM or CPU, the total virtualization host specifications. You can also specify network charges related to hosting an inbound and outbound data charge, and also your peak and average ratio of data. You can also specify factors related to the cost of labor associated with maintaining your current fleet. For this example, we're going to stay in basic mode. Once you are happy with the data about your existing fleet, click the Calculate TCO button at the bottom of the page to begin the calculation process. The resulting calculation is broken up into several sections. There's an overall executive summary at the top that displays the estimated total savings as a percentage of your existing bill and also in dollar values. It also provides a 3-year cost breakdown showing side-by-side on-premise versus AWS. The environment details show the specifications that you provided about your off-cloud environment and the environment that the system has matched it to in AWS as closely as possible. So this is some cost breakdowns based off cloud server and compute for EC2, storage, off cloud, and also EBS, and also network charges. The second half of the report is broken into 4 sections. The first section, called Calculations, provides a fine-grained breakdown of all the data points collected and the calculations used to reach the recommended savings in the previous part of the report. The final section of calculations displays total costs associated with AWS support if activated on the account. The second section, called methodology, provides the overall methodology used by the TCO calculator, how on and off-premise environments are compared, and the total calculations involved. The third section, called assumptions, provides some of the assumptions that were made about how an off-cloud environment might transition into AWS. And finally, the last section contains frequently asked questions about how the calculator works and the assumptions and methodologies used. At this point, if you're happy with the outcome of the TCO calculator and wish to share the results, you can select the Download Report button, which will allow you to generate a fully complete PDF report of all of the data shown here in the web browser that can be shared with internal members of your team or even with your customers directly.
The AWS Billing and Cost Management Console is a tool you can use to pay your AWS bill, monitor costs, and visualize your AWS spend. It provides important features, including cost visualization, customized alerts on spending limits, detailed billing reports, and consolidating billing. For instance, the Cost Explorer tool provides graphs to review your spending visually, or you can get detailed billing reports that break down your costs by the hour or month, by product or product resource, or by tags that you define yourself. If you have multiple AWS accounts, you can consolidate multiple linked accounts under one payer account. Consolidated billing is designed to simplify your accounting and let you take advantage of lower price usage tiers for many AWS services. This concludes Module 4. In review, we have explored use cases for web, mobile, and social applications, and big data. We have seen how the AWS cloud architectures compare to traditional infrastructures, and we have associated these specific AWS services used to build each solution. Each solution represents an opportunity for migration to AWS services, and we have discussed the technical implications relating to migrating technology to AWS. We have also learned about pricing tools to help you estimate AWS costs and make the most efficient and cost-effective choices for your AWS services. AWS provides many resources to identify migration and pricing strategies to help customers get started in cloud computing and leverage its efficiencies. You may want to explore these in the APN portal. Before you move on to Module 5, please answer the following practice test questions. These questions will help you prepare for the accreditation test, but are not scored. Correct. AWS is compatible with all devices and the most popular mobile platforms, including SDKs for iOS and Android. Correct. Amazon S3 storage service can be used to upload large data sets. You can make the most of the available bandwidth by uploading data into S3 in parallel from multiple clients. For very large data sets, it may be faster to transfer that data from your own storage device using import-export. You can also use S3 as a scratch area. a traditional web architecture, all of the components are tightly coupled to one another, which means that you can't easily insert new servers to handle unexpected traffic, and the entire system has a limit to how much it can handle. AWS provides an elastic and scalable platform for your web and mobile apps, giving you flexibility to meet peak demands and reduce costs when those resources are not required. Correct. AWS uses a utility-based model, where you pay only for what you use. Each service is priced independently, so you choose only the services you need. You can start or stop any service at any time. Congratulations! You have completed Module 4, covering architectures and solutions for web and mobile and big data. Next, continue on to Module 5, security and compliance.